Hello, welcome to Let's Fix Logging Once and for All. To review the abstract so we know we're on the right presentation, we describe a modification to the Linux kernel which gives an SRE control over the combined bandwidth of logging on a node of a distributed system while providing a way for the logging source owner, container, or service to control what happens when the bandwidth limit is hit. Now, why do we care about this? We care because nodes can become unstable when one or more processes consume the disk or network resources of a node excuse me, with unintended behaviors or malicious code or bugs in the platform. And we want to separate that policy of what happens when we hit the rate limit from the SRE's control of the rate limit so that the application owners maintain behaviors in the face of those limits. My name is Peter Portante. I'm a senior principal software engineer at Red Hat for the last 10 years. So something cool I've done, 7 club passing. That's 2 clubs in each person's hands and 3 in the air, which is really fun. For me, P99 is new and hopeful. I'm really interested in this conference and see how it turns out. I enjoy yard work and puttering around the house, and I love to juggle clubs. So let's just take a look at the solution to this logging problem from 30,000 feet. We restore behavioral control for logging on a node to the SRE. Today, the SRE has no ability to control that. And the SRE should be able to set a limit for the total logging rate on a node and walk away knowing that the operation of that node is not going to exceed that. And secondly, in the face of that limit, applications should retain control of the behavior of their applications when those limits are hit. And what I mean by that is if the application doesn't care about the logs they emit and they can be thrown away, then so be it. Or if they do care about the logs and they want their application to be slowed down to make sure the logs get captured, then they get to pick and choose how that behavior happens. And so the way we go about this is we set a node rate limit using an opt-in, if you will, bandwidth gate for file descriptors. And the idea being is that the SRE sets the limit, it's system-wide, it includes an interval, so maybe it's 100 megabytes a second, maybe it's 10 megabytes a minute, however the SRE wants to describe the interval and the breakdown. And then we place the gate at the beginning of the write system call. Excuse me. So write system calls move no data into their target file descriptors if the bandwidth limits have been hit. And then the SRE directs the frameworks that we all know and love today, systemd, podman, conmon, etc., to use that gate that's been set up. The behavioral policies for the application are set and ahead of time, and the application owner, the one who's going to run the application or request it be run on the platform, gets to pick one of 2 policies, and potentially a third, but one of 2 policies, drop or block. And the idea being with drop is very simple. If the write system call sees that the amount of data in that interval would be exceeded by the write, it will issue and write whatever bytes it can up to the limit of that interval, and then after that, it'll just drop the rest of the bytes on the ground. And so the write system call will still return that it wrote, 1,000 bytes or whatever it was that was in the write, but only that data that fits in that interval will get written to the file descriptor. Conversely, the block will only write, again, the data that fits in that interval, But any remaining data, it'll return as unwritten. So the write system call semantics are that the amount of bytes written by the write system call are returned. And so we leverage that semantic to return only that can be written. And if the write system call can't write any bytes in the interval, then it will block. And the big key to all this is that no data from the application's buffer is transmitted to or moved to the file descriptor excuse me, as a result of the write call if the bandwidth limit set by the SRE is already met. And then the frameworks that we all use here, systemd, podman, conmon, etc., those frameworks are the ones that take the request from the user or the application owner to set the policy and apply that into the framework. Okay, so that's the solution. That's the whole thing. But we got to answer the question, why is this a problem now? And I think that's really the big deal to go after, is to take a look at the three pieces I think that combined make this a problem to be solved. The first one is arguably the biggest one and the biggest problem, which is that most container runtimes, and this is actually true of systemd as well, but it's a bigger problem for container runtimes, they capture or they do a byte capture and interpret the byte stream of standard out and standard error by default and write that data to disk first. Now that's really an important piece to chew on a little bit here. Byte capture and interpret. That means it's comparing every single byte in the stream and it's taking action on what it finds in the stream. And then it takes all that data and it writes it to disk. And I think if you look in the slide notes along with this, you'll see a reference to an analysis of how Conmon does that. Docker does something similar as well. And that's a big problem because by writing to the disk first, all of the data from standard out, standard error interpreted, you spend CPU resources to do it, for one, and there's no way for anybody to insert some kind of a back pressure because the writes to disk no back pressure can be given to the Conmon writer through the file system. The second thing that's conspiring with all this is what I call the densification of application. So when you have high core count, high number of sockets, people love hyperthreads for some reason, the node concurrency that you can deploy to today can easily generate more logs than some local disk bandwidth that's available, or even the network attached to the system. And that's an imbalance that the SRE has no control over right now. They can try to size and make the disk bigger, or what they end up doing is going against the densification. They lower the number of applications to try to meet this. And that's not a good way for the system to operate, because the goal is to leverage and get the most out of your compute resources. And the third thing, which is newish today, is that folks who write an application and put it into a container often run that separate from the folks that, or want to have that run by folks who are running a platform to deploy it, and they're entirely different organizations, entities, and the person and people who run the SREs, who run those applications, don't necessarily have control over how that application is written. And so when you take these three things combined and you put them together, you make a large problem for the SRE, because they have no way of controlling the application on that node to maintain the node stability. So I love this little GIF. There's a gifmemes.io. If you want to go play with how it works, you can do all this stuff. This is a great example of what happens to logging systems. Folks have written all kinds of way of dealing with logs. Let's make the backend sync faster. Let's fix how quickly they're read from disk. Let's be more efficient and write it in Rust, or let's be less efficient and write it in some interpretive language. However you want to go do it, and however they do it in development and staging, it looks great, and then they get to production, and production just kills them for whatever reason. And there's many reasons. They try their system on production, and it usually falls over, and it's usually like a fall over a cliff thing, because what happens is all of these problems sort of build up and then come crashing down at once. So let's take a look and get into container logging a little bit to see how this actually works. So I'm going to present this other slide. This is on Lucidchart here. So just as a review for folks, in case they don't have an understanding here of this or experience with this, in the Kubernetes environment, CRI-O is the underlying container runtime, and the way that's done, or with logs that is every container, now container is an abstraction, every container has two pipes associated with it, standard out and standard error, that are created by a process called Conmon. And Conmon is responsible for creating all the processes in that container. And so if we move to step 2 over here, you might have a one process in there. You could have 3 processes in that container, but every process has threads, one or more threads in it. And it's the threads, the threads are the execution entity that are scheduled by the Linux kernel. It's the threads that write to the pipes, those 2 pipes. And so what happens is, combined, you have n containers on a node. So maybe you're looking, you have a small node and you want to run 10 containers. You could be doing a large node, 200, 500 containers. But again, it's not pods, it's containers. So pods are just an abstraction Kubernetes around containers. It's containers that the scaling piece for logging comes in. And so for every container, you have 2 pipes, and you have these Conmon processes running. And then you've got some disk you're logging to, and those Conmon processes will consume, or can consume, the available disk bandwidth for that disk. And then what you also have is typically some kind of a log scraper that's reading from those log files. It could be something like a FluentD or an rsyslog or Vector, or I don't know, pick your thing, Graylog, whatever the log scraper that folks want to go use, and they're reading from those files. And so that reader or readers, depending, they have to be able to keep up with whatever rate the containers can write to. And so now you begin a competition with them. And also, by the way, the local Kubernetes kubectl log, or if you're on OpenShift, OC logs, or if you're just running Podman yourself, Podman logs, you have, those are scrapers that are also reading from the disk. And so this is the picture where you can see these 2 pipes right here, which are not really pipes, they're the available bandwidth of the disk, is what becomes contentious on the node. So we're going to skip to the next thing real quick. I'm going to go into how the containers write to the pipes, and I want to show you just a little bit real quick. What happens is every thread is within a container. So these are 4 threads within a container across 3 different processes. 2 threads are in the same process. Every thread is going to have some amount of data to write, and the way this works is that they just take their data, they write it into their pipe, and so up till time T3, you've got some data written into standard out, some into standard error. On time T4, you get some additional data written, and then at time T5 here, Conmon starts to wake up and see that data's in the pipe, and it starts to read stuff out, pull stuff out. And so it pulls out at 8 kilobytes at a time, and it's going to flip back and forth between standard out and standard error. And it's going to suck out 8 kilobytes of data each time. and rocking back and forth between the two, and finally it'll fill up that log file after having read all the data. And you can see I kept the colors in here to show that even though, because it's reading in 8 kilobyte chunks and it's alternating back and forth between standard error and standard out, you can see that a 8 kilobyte standard error chunk got written, and then the rest of that standard error is interleaved by 8 kilobytes of standard out data, and then it goes back to standard error data for the rest of the data. So that's what the on-disk format is, and the Conmon process is doing nothing but reading from the pipe synchronously and writing to disk synchronously. So these slides are linked. This lucid chart is linked in the slides, so you can go and view them yourself over here, these two links. So let's go to the solution at a little bit lower level to see what we do here. So first, we got to answer the question, why do we do this in the kernel, and why are we proposing in the kernel? One very simple reason, is we want to make sure that the data is kept from moving when not necessary. So both Conmon and systemd could implement a mechanism like we're talking about by doing it in user space and collaborating with different folks with shared memory and all kinds of data. But in order for a user space process to know anything about the data coming out of those logging entities, they have to have the data transferred to them. And so already that means that you have to pay for that data transfer. And systemd already has part of the solution. If you look at systemd, it comes with a default limit on how fast it will read. And systemd's got a pretty good solution today compared to Conmon and container logging and cryo, because all of the data for systemd is not written to disk first. The processes run by systemd first send the data over a socket to journald, and then journald writes it to disk. And so there's not this, there's a single choke point where it can do all the math for bandwidth, but it doesn't give you control over drop versus block. So the applications can't say, hey, I want to just ignore my data. They only get block there, and it's a very severe by default. And then Conmon could do this, but now if you implement one solution in systemd and one in Conmon, and everybody comes up with their own thing, the SRE ends up with a difficult management process. And the whole point of this solution is to give the SRE one place to set the logging limit, while avoiding any unnecessary resource usage along the way to handle those logs. So very simply, you could have a little sysconfig file with a logging bandwidth set in it. You set an interval, you set an amount, and the frameworks conspire to read that and participate in that bandwidth gate. And the way we're looking at doing this is using eBPF. We have a person at Red Hat people at Red Hat who are looking at adding and proposing a hook point at the beginning of the write system call to allow for an eBPF script to be done, and that way we can experiment with the right eBPF script and policies and enforcement ahead of time, and then the frameworks like systemd, cryo, podman, and Conmon, they can opt in when they're ready to participate in the SRE limit set. And then those same frameworks, systemd, podman, be very simple to add into the service file, the logging policy, drop, block, etc., and have podman on the command line set that policy for it. And in Kubernetes, you can do that same thing with the container spec where you add that drop versus block to the logging policy going forward. And the big key to all this is when you go back to this view of how data is written, we want to prevent these threads P0 through P2. We want these threads not to transfer any data into these standard out, standard error pipes if that bandwidth limit is hit. And that's really the key point of all this. So to recap, we want to institute a node logging limit controlled by the SRE. So we want to give the SRE complete control over the node's behavior. We want to give the application owners the ability to determine what to do when that rate limit is hit. So I don't care, I want to drop, or like maybe I want to block standard error, I want to drop standard out. Whatever you want to go set, the application owners get to choose what happens. And then we want to make sure that the way this gate is placed is it's at the very beginning before data is transferred off the process. And then we want to do this in the kernel so that we can offer this gate to be shared across multiple subsystems that SREs all run at the same time. And that's it. Thank you very much.